The most popular and prevalent protocol stack is TCP/IP, which stands for the Transmission Control Protocol Internet Protocol. TCP/IP is called a protocol stack because it contains dozens of protocols, but it's named after the two most important protocols. TCP/IP is designed to run on whatever data link layer or physical layer protocols are implemented within a local area network, and therefore doesn't include protocols at those levels. It focuses on inter-network technologies. TCP/IP is designed to work over the internet hardware with all those vendor networks to deliver services to users. As you can see here, TCP/IP does not neatly map to the OSI model, but it does perform all of the key functions. The TCP/IP application layer does the job of the application and presentation layers and some of the session layer functions I described under the OSI model to provide web, email, FTP, and several other services. It formats the user's application request, handles encryption and translation services. Below that, either TCP or UDP protocols handle the transport layer functions, providing host-to-host transportation. This roughly maps to the OSI transport layer with some of the session activities. TCP/IP handles setting up, maintaining, and tearing down sessions when a user connects to a remote server or other computer. It requests a session, transfers your information, and then tears down or disconnects the session, allowing someone else to use the system. While servers can typically handle hundreds or even thousands of concurrent sessions, they don't have infinite resources. And that's why denial of service attacks are as successful as they are. They deny legitimate users access to servers by constantly requesting sessions, but not doing anything until the session times out. UDP is used primarily for short, quick communications, so it's considered connectionless in that it doesn't establish sessions, it just delivers these quick messages. The transport layer also handles fragmentation, which is like packetization, breaking larger messages up into smaller ones when they exceed what the protocol can handle. TCP also handles error checking and correction for the protocol stack, requesting replacement packets when they arrive corrupted or are missing. The network or internet layer, with its familiar IP protocol, handles the communications between networks across the internet. The IP layer is responsible for addressing and routing of packages across multiple networks. To view your IP address on your personal computer, open a command window and type ipconfig/all. The first thing you may notice is the system has two or more IP addresses, in addition to a MAC address, one IPv4 address and one IPv6, representing version 4 and version 6. But more on that in a second. The default gateway is your internet router's IPv4 and IPv6 addresses. The physical layer is the data link layer address for your system, the MAC address. It's listed in hexadecimal, which is base 16. IP version 4 addresses are commonly written in dotted decimal notation, 4 sets of 3-digit numbers ranging from 000 to 255, each representing an 8-bit digital equivalent. Most IP addresses are assigned to an organization or residence by an internet service provider in blocks. The problem is that the internet is quickly running out of addresses, since many blocks of addresses are reserved or issued in large quantities to organizations that may not need all of the addresses. There are two ways to solve this problem: a quick temporary fix and a more permanent solution. The temporary fix is to use private addressing inside of an organization and public addressing outside. The public address is the IP address assigned to the organization or residence by the ISP, but the organization can assign its own addresses for internal use. There are currently 3 ranges of private IPv4 addresses that are reserved by the protocol for use by anyone. The first gives the user over 64,000 addresses they can use. This is similar to the old-style Class B address, where the user can choose any value for the last 2 octets or sets of numbers. The second example gives the user the equivalent of 17 Class B addresses, or over 1 million addresses in total, while the third gives the user the equivalent of a Class A address, where the user can assign any value for the last 3 octets, resulting in over 16.75 million addresses. You can use any one or a combination of these, as these addresses cannot be routed over the internet, as they are reserved. You simply have to translate these addresses when you want to access an external source. Fortunately, a gateway, like a cable internet router, can do this for you. A portion of the IP version 4 addressing involves specifying which parts of the address belong to the network and which belong to actual computers. As organizations are commonly assigned more addresses than they need, or if they're using private addressing, they may want to use part of the address to specify a subordinate network or subnet, and part to specify the machines on that address. Subnetting is therefore the process of internally dividing an IP address block into smaller blocks for ease of use. Let's say, for example, I have a network in a 10-story building, with each floor having its own sub-network. While using the dotted decimal notation, I could specify the floor using the 3rd octet, representing the subnet, and then specify the machines or computers on that floor using the last octet. But from the network protocol's perspective, all I need to specify is what part of the address is the client's address and what part is the network address. That is done with the subnet mask. While it's not required, you can use octets to specify subnets. Just realize you're manipulating the decimal equivalent of a binary number. At the binary level, a 1 means that part of the IP address is part of the network address, and a 0 is part of the computer address. You can see the 3 ways of specifying the subnet mask here. You can view the IP address configuration on your computer by looking at the IPv4 properties on your Ethernet adapter under Computer Networking. However, if the first box, Obtain an IP address automatically, is checked, all of your configurations are automatically assigned by the network, specifically by a device serving as a DHCP server. DHCP is the Dynamic Host Configuration Protocol, one of the TCP/IP protocols responsible for managing IP addresses. While you want the computers that provide services to have static or unchanging addresses, you may want to dynamically assign protocols to client computers to allow better management of the addresses. While you will want computers that provide services to have static or unchanging addresses, you may want to dynamically assign addresses to client computers to allow better management of your addresses. When using private addressing, you will find it necessary to translate those addresses to an external IP address that can be routed across the internet. There are 2 methods of address translation, one of which is the simple mapping of internal private addressing to ISP-assigned external public addresses. This is known as Network Address Translation, or NAT, and is primarily used for security purposes. It really doesn't help the number of available external internet addresses issue, as you need an external address for every internal address. Port address translation, on the other hand, is something you automatically do anyway. Even if you are using an external public address, every time you open a different web browser or browser tab and go to a different website, goes with which browser or browser tab. Your system attaches a port number to the end of your IP address, and that is used to associate the requested information with a specific browser or browser tab. A gateway can do the same thing, allowing hundreds of internal users, using private addressing to use very few external IP addresses as shown here. The permanent fix to the IP version 4 address shortage is the implementation of IP version 6, which will provide over 4.3 billion addresses. If we use it with private addressing, there should be no shortfall of addresses for a long time. An IP version 6 address is written in hexadecimal and can be abbreviated by removing long strings of zeros and replacing them with a double colon. IPv6 also has its own range of internal private addresses, making it the best long-term solution to the internet address problem. As each IP packet works its way across multiple networks, each router on the edge of the network reads the packet and passes it to the appropriate direction. Routers build or are programmed with routing tables which can tell it which outgoing port to send a packet to. In the event an address comes in that isn't in the routing table, the routing has a default next hop router to pass it to. Remember, IP packets are in reality a long string of bits, not neat boxes. TCP/IP relies on whatever local area network protocol is being used for what is known as the subnet layers, also known as the network interface layers, to provide data link layer and physical layer functions. Most local area networks use a protocol called Ethernet, the IEEE 802.3 protocol, which was specifically designed to support local area networking. You can run a local area network using Ethernet without any internet connectivity. Ethernet is the data link layer or subnet layer protocol, and it's not part of the TCP/IP protocol stack. Ethernet uses a frame, which includes a preamble that identifies the following bits as part of an Ethernet frame: the designation Ethernet address, the source Ethernet address, the type of Ethernet frame and overall length of the packet, and the user data, finally followed by a frame check sequence for error checking. Ethernet uses a communication technique called CSMACD, which stands for Carrier Sense Multiple Access with Collision Detection. Carrier Sense means the computer listens to the network to see if another computer is transmitting. If there's not, it transmits. Multiple access means just that. Multiple computers can access the network at the same time, and it's first come, first transmits. Collision detection means that the computers can recognize when another computer tried to transmit at the same time. When that happens, both computers select a random number, waits that many milliseconds, and then retries. Since all computers involved are selecting random number, odds of a second collision are small, but the software is prepared to keep selecting larger and larger random numbers until the collision is resolved. With a switched network, Ethernet still performs these checks, but they seldom collide anymore due to switching. When local area networks first came out, there were other protocols that used different communications techniques. But since Ethernet became the dominant local area network protocol, they're not imported anymore. In the next lecture, I'll discuss securing internet services and the web.